if we want to figure out when the slope of the tangent line is -1/4, we need to find the slope of the tangent line, right? We need to find an equation that represents that. And what's the method that we're using to find the slope of the tangent line?
F of x over x.
Well, f of x plus h minus f of x over h, right? And it's a limit as h approaches 0 of that. This is the limit of the difference quotient. This is the derivative, right? And remember, we talked about the derivative is the slope of the tangent line. So we want to find the derivative using this formula of 1 over x. So that ought to be 1 over x plus h minus 1 over x all over h with a limit as h approaches 0. Everybody good with that or no?
Yeah.
All right, cool. So then all we need to do is get our common denominator, which should be x times x plus h. We're going to get x over x times x plus h, and then minus an x plus h. Right? We have an x over x that we multiply here, and an x plus h over x plus h that we multiply here. Combine them together into one fraction. Don't forget your limit, like I almost did. X minus x cancels out, and this just becomes minus h. And the h goes into the denominator, xh times x plus h. Everybody okay with that or no?
Yes.
All right, the h's will cancel, and we end up with the limit as h approaches 0 of -1 over x times x plus h. And as h goes towards 0, what does that become?
X times x squared.
Yeah, it should become -1 over x squared. Right. So this is the derivative of 1 over x. And we want to know, when does that derivative, when is the slope of this tangent line equal to -1/4? So we should be able to solve that for x. What does that give us if we solve for x? X equals
2.
positive or -2, right? Don't forget the -2. So at x equals 2 and at x equals -2, that's when the tangent line has a slope of -1/4. So would it be possible for us to write the equation of the line at x equals 2 and the equation of the line at -2? That'd be the point 2 comma half, right? And the point -2 comma -1/2.
Yeah.
Yep. And so we should end up getting y minus 1/2 equals 2 times x minus 2, and y plus 1/2 equals -2 times x plus 2. Those would be the actual equations of the tangent line. And if we went in and graphed this in Desmos, y minus 1/2 equals 2 times x minus 2. I gotta actually graph the actual function first. 1 over x, and y minus 1/2 equals 2 times x minus 2. Is that what it was? 2 times x minus 2?
Yes.
That doesn't look right. What did we do wrong? We must have done something wrong. Y minus 1/2 equals 2 times x minus 2. That certainly doesn't look like the slope of the tangent line at 2. Oh, that's because the slope isn't 2. Ah, why did I write a 2 there? Our slope is not 2. What is our slope?
Negative 1/4.
Yeah, our slope is negative 1/4. Sorry, I don't know why I put 2's there. There should be negative 1/4. I wonder that didn't make any sense. So if we change those to negative 1/4, that ought to be better. Negative 0.25. There we go. And then this one, y plus a half equals 0.25 times x plus 2. Is it x plus 2?
You forgot the negative.
Oh, I forgot the negative. Man, I'm struggling this morning. There we go. That looks good now. Look at that. At negative 2 and at 2, they touch their tangent lines, and it sure looks like that's the slope of those functions at that exact point. Good or no?
Good.
Good.
Other than my horrible transgressions there of putting in 2 and negative 2 for the slope, even though they gave us the slope. All right. So next thing we want to talk very briefly about is what a normal line is. So a normal line is just a line that is perpendicular to the tangent line at some point on a function. So if I was looking at this previous one, right, the normal line would just be perpendicular at negative 2 or perpendicular at 2, which would make the slope, instead of negative 1/4, the slope would be, what would the slope be if we were perpendicular?
4.
Should be 4, right? And we can see that's perpendicular there, right? That's the normal line. Same thing we could do with this one if we wanted to. Change that into 4, and it's perpendicular there at negative 2. So those are normal lines. And normal lines are the lines that are perpendicular to our function. Perpendicular to the tangent line at some point. So if I want to find the equation of a normal line to a function, the first thing we're going to need to do is find the slope of the tangent line. So this should have a slope that is the opposite reciprocal of the tangent line. So if we can find the slope of the tangent line, we should be able to figure out what the slope of the normal line is. You all agree with that?
Yes.
All right. So we've now got the limit as h approaches 0 of x plus h squared plus 1 over x plus h minus x squared plus 1 over x all over h. That's how to find our slope of the tangent line, right?
I think you forgot the positive. You wrote a negative instead in the numerator.
Oh, yes, I did. Look at that. Perfect. Thank you. And then how are we going to do this?
Multiply x plus h times x plus h, and then after that, multiply the negative by the parentheses. Yeah, just
Okay,
like
so distribute the
simplify.
negative through.
Yeah, just distribute them first, and then
We're going to need like a common denominator in here, right? And to me, it looks like that's going to be a little bit of a pain to find a common denominator, right? I mean, it's not hard to find the denominator that's in common. It's x plus h times x. That means I got to multiply this by x and x plus h, this by x over x, this by x and x plus h over x and x plus h, and this by x plus h over x plus h. So it's like a lot of multiplication, but I could, if I wanted to, since this is a limit, separate it into 2 different limits, couldn't I? Can I separate it into one that doesn't have all the annoying denominators and one that does have all the annoying denominators?
Yes.
Yeah. Why not? Might as well. So what does this one become? In fact, I think the other day we might have done this one already, but it's all right. We'll do it again. the limit as h approaches 0 of x squared plus 2xh minus x squared over h. And we can cancel out the x squareds.
What about 8 plus h squared?
Oh, yeah, I don't know. Why didn't I write the h? I don't know. I'm struggling this morning. Probably because I'm trying to get us caught up and I'm trying to go too fast. Plus h squared minus the x squared. All right. Now we'll cancel out these x squareds. And now we can divide everything by the h, which will give us 2x plus h, which gives us what? As h approaches 0, just
2x.
2x. And then what about this one? I swear we just did that one on the previous page, didn't we? Did we do that one on the previous page?
Okay, yeah, we did.
Came out to be minus 1 over x squared, right?
Mm-hmm.
All right. So we are interested in the slope of the normal line at x equals 1. So let's figure out the slope of the tangent line at x equals 1. What does that give us? 2 minus 1, which is 1.
Yeah.
So the slope of the tangent line is 1, which tells us that the slope of the normal line, which is perpendicular to that, ought to be
Negative 1.
negative 1. And to write the equation of the line, we need the slope and we need the point. So we got to find what's f of 1. And f of 1 ought to be 1 plus 1, or 2. So we have the point 1 comma 2 with a slope of negative 1, which ought to give us y minus 2 equals negative x minus 1. Everybody good with that or no?
Good.
All right, and let's real quickly look on here. What do we have? We had x squared plus 1 over x. All right. So there's x squared plus 1 over x. And we had y minus 2 equals negative x minus 1. And at x equals 1, it sure looks like that's perpendicular to the slope of this function there. We could test and make sure just by kind of looking at the actual line here. If I got rid of the negative 1 and made it a positive 1, that should give us the tangent line. Sure looks like those two lines are perpendicular, right? We know they are because their slopes are opposite reciprocals, but that purple one definitely looks like the tangent line. And so the one we've got is definitely the normal line. Good or no?
Good.
All right, cool. Everybody feel all right about this stuff? Could do one more. Let's do one more. See if we can write the equation of the line tangent to root x and the normal line to root x at x equals 4. Any thoughts on how we might do that? What should we do? Limit as
X approaches 0.
h approaches 0, right?
I thought X said H, you know what I mean?
Yeah. Definitely. Makes sense. Root x plus h minus root x all over h. How do we deal with that?
Square everything.
We can't just square everything because that changes the function. This is an indeterminate limit. So what are the ways we've learned to deal with indeterminate limits?
Multiply by the conjugate.
Multiply by the conjugate. That's one way. Let's see if that works. What do we get in the numerator? Root x plus h times root x plus h is
X plus h.
x plus h. Root x plus h times root x should cancel with root x plus h times negative root x.
Yeah.
And then root x or negative root x times root x
Minus
is minus x, giving us h times root x plus h plus root x. What happens in the numerator?
X's cancel.
What's that? The x's cancel, you said? So we got h over h and then root x plus h plus root x. And again, our h's will cancel. And as h approaches 0, what do we get?
2 times root of x.
1 over 2 root x. Everybody good or no?
Yeah.
All right, so we need to evaluate this at x equals 4. What does that give us at x equals 4?
1/4.
1/4. So that's the slope. Tangent line. And what's the slope of the normal line?
-4.
Should be -4. Good. And what's the coordinates of the point? F of 4 is
2.
2. So we should end up with y minus 2 equals 1/4 times x minus 4. And y minus 2 equals -4 times x minus 4. Using point slope form. Everybody good with those two?
Yeah.
And real quickly, we'll take a look at them on the graph. So we had square root of x, right? And we had y minus 2 equals 1/4 of x minus 4. And that sure looks like a tangent line at x equals 4, doesn't it? It's touching the graph right there, but staying on one side of it. And that would definitely mean that the other one ought to be the normal line. And it sure looks like it is. Good or no?
Good.
All right. So that's all we're going to do with these practice ones of the limit as h approaches 0 type. What we're going to do now, and you're going to have a homework assignment where you have to do this, which will be due tomorrow. We're going to take this idea of the slope of the tangent line, or what we call the derivative, being this limit, and see if we can apply it to some other generic functions to write some rules that might help us to find derivatives a little bit more easily. So that's going to be our goal for the rest of the day today. Sound good? The first rule that we're going to prove is the derivative of a constant. Okay. We talked about this, right, the other day, where we just drew, I think, a horizontal line and said its derivative should be 0 because the slope of it is 0. But if we wanted to go through and say that we were trying to take the derivative, and I'm going to tell you right now, this notation d dx means derivative with respect to x. Okay, so the derivative, that's what the d in the numerator is telling us, and then we're doing it with respect to x because there's an x dx in that, there's that dx down there in the denominator. We're going to talk more about the notation later, but d dx means take the derivative with respect to x, which means that the variable that you're dealing with in this problem is an x variable. If I wrote this d dy, that would mean we'd be taking the derivative with respect to y, and that the variable in the problem would be a y. I could make that anything. It could be d d theta, and my variable would be theta, or it could be d dz, and then my variable would be z. Okay? So in this case, It's with respect to x. And it's of a constant. So if my function, let's say, is y equals some constant c, what is f of x plus h? Replace all of the x's in this function with x plus h's. Well, what do you get if you replace all the x's with x plus h's? You should just get c, right? There's no x's to replace, are there? And this is f of x equals some constant, some number like 7 or 2 or -8. There's no x's to replace with x plus h's, so f of x plus h is also just c, and f of x is just c. So you end up with that constant minus that constant in the numerator, which gives you a limit as h approaches 0 of 0 over h, which is the limit as h approaches 0 of 0, which is 0, which tells us that the derivative of any constant is 0. Does that make sense or no? Yeah, no, maybe.
So why don't we treat it as an indeterminate?
In the 0 over 0? Oh, sorry, 0 over h?
Yeah.
Well, we are, but what we're doing is we're simplifying it down. So is there a way to simplify 0 divided by h before you plug in this 0 for h? 0 divided by anything, as long as this thing in the denominator is not 0, is going to be 0, right?
Oh, okay. So we're just
Right,
not
and this
considering.
h value is never actually going to be 0 because h is approaching 0.
Got it.
And we could just sort of intuitively think about this as, think of a function y equals 2. There's y equals 2, right? Well, the derivative is the slope of the tangent line at any point. Well, what's the slope of this thing at any point? Its slope is always
2. Wait, 0, yeah.
0, right? Because it's horizontal. It's not rising. The rise is 0, and the run is whatever you choose it to be for where you're finding the slope. The slope is 0. Everybody okay with that or no?
Yes.
Okay. All right, now we're going to do another one that's super simple looking, right? Nice and simple looking. X to the n power. Okay. So anything like x squared or x to the third or x to the eighth or anything like that. So what I've done, you can see there hopefully, is I've written the limit as h approaches 0 of x plus h to the n power, right? That'd be f of x plus h, minus f of x all over h. Everybody good with this first piece right here? Or no?
Yes.
All right. Everybody good with the second piece? Where'd the second piece come from? Where'd all this crap come from?
Expanding the numerator.
Yeah, expanding the numerator. That is the binomial theorem expansion. This is the binomial theorem right here. Right? The binomial theorem tells you how to expand out a plus b to the n power. These coefficients, this n and this n times n minus 1 over 2 factorial and n times n minus 1 times n minus 2 over 3 factorial, those are just the numbers that come up in Pascal's triangle. That's just a way to find each of the numbers for any particular value of n that we were at. So if we're in the fifth row, then this would be 5, and then 5 times 5 minus 1 divided by 2, and then 5 times 5 minus 1 times 5 minus 2 divided by 3 times 2 times 1, and so on. You don't need to know exactly how all of these things were derived and where they came from for this particular class. Just accept that I've done this correctly. Everybody okay with accepting that I have expanded that x plus h to the n correctly?
Yes.
All right, spectacular. So now what's our next step normally?
Can't like solve it, simplify it.
All right, and how do we always simplify it first? Everything that didn't have an h term in it should do what?
Cancel out.
Cancel out, right? So there's x to the n and minus x to the n. Everything else has an h in it, I think, right?
Yeah. Oh yeah, I think yeah, H can cancel out.
They should all have an h. So then we should be able to divide everything in the numerator by h. So n x to the n minus 1 times h should just become n x to the n minus 1. And then the next one should become plus n times n minus 1 over 2 factorial times, that didn't look like that. There we go. Times x to the n minus 2 times just h, right? Plus a bunch of other stuff that all has h in it, right? A bunch of other terms with h in them. True? I'm not going to write them all out. So what happens as h approaches 0? Well, n times x to the n minus 1 just stays as n times x to the n minus 1. But what about this term?
Becomes 0.
It becomes 0 because it's getting multiplied by h. And what about all these other terms with an h in them?
0.
They're all going to become zeros because they have an h in them. And as h approaches 0, when you multiply by that 0, it goes away. So this tells us that if I want to take the derivative of x to the n power, the answer is just n x to the n minus 1 power. Okay. The derivative of x to the n is n x to the n minus 1. This rule is called the power rule. It is a very important rule. It is a rule you need to know and have memorized. And the derivative of x to the n is n x to the n minus 1. Everybody okay with how we got to that?
Yeah.
All right, cool. So let's apply this rule. I'm going to start talking about different notations for derivatives as we go through. Okay? So remember, this means the derivative with respect to x. It means the variable in there is x. So the derivative with respect to x of x to the n is n x to the n minus 1. This right here, f prime of x, means the derivative of f of x. So f prime of x is the derivative of f of x. We want to find that for f of x equals x to the 7th. What should f prime of x be? How do we do this? I have x to the n, right? So the derivative should be n, 7, x to the n minus 1, or 7x to the 6th. That's it. That's the derivative of x to the 7th power. Easy enough?
Yeah.
Any questions on that?
No.
All right. That's a lot better than doing this, right? The limit as h approaches 0 of x plus h to the 7th minus x to the 7th over h, and then expanding out x plus h to the 7th to x to the 7th plus 7x to the 6th h, and so on, right? And having to evaluate all that out. This is much easier, isn't it?
Very much so.
Yeah, it'd be good to know how to do it this way. All right. This y prime, that means the derivative of y. So what is y prime? If y is x to the 4th, y prime ought to be, using the power rule,
4x to the 3rd.
4x to the 3rd. Easy enough?
Yeah.
Yes.
All right. What should the derivative with respect to x of x to the 50th power be?
50x to the 49.
50x to the 49. That's simple. Right. Much easier than using that limit. The limit is where this comes from, but we can make a generic rule by using the limit as h approaches 0 for the generic x to the n. Gives us this really convenient rule that makes these derivatives exceptionally easy. Everybody okay with that?
Yep.
All right. Next thing that we want to do is recognize that if I want to take the derivative of a constant times some function u, right? U is just some function u of x. And rather than sometimes we use f of x, sometimes we'll use u or v of x. If I want to take a derivative of a constant times a function, it's just the constant times the derivative of the function. And with any luck, that should make sense because what is a derivative? A derivative is just this limit. And what happens if I have a constant within a limit? What can I do with that constant?
Bring it in front of the limit.
Right, I can take those constants and move them to the front of the limit. So it's the same basic concept there. If I'm taking a derivative and I have a constant in it, I can just pull that constant out, take the derivative, and then remultiply that constant at the end. Does that make sense to everybody?
Yes.
All right, cool. So if I want to take the derivative of 5x to the 4th, that should be 5 times the derivative of x to the 4th, which is 5 times what?
4x to the 3rd.
Perfect, which gives us 20x to the 3rd. And we'll note that we could just multiply this power by the constant that's out in front. That gives us this 20, and that should do it. So what's this? This means the derivative. Another notation. Lots of different notations. This means the derivative with respect to x of 11x to the 8th.
11 times x of 8. All right.
How do we take the derivative of x to the 8th? That ought to be 8x to the 7th. So this gives us 88x to the 7th. And you don't need to write this step in here anymore. All right, you can just multiply the 11 times the 8 and get 88 and drop the power by 1. So anytime it's a power, multiply the power by the coefficient and then drop the power by 1. Easy enough?
Yep.
All right. If I have multiple functions being added together or subtracted, okay, and I want the derivative of it, I can just take the derivative of each one separately and then add or subtract them together. So if I want f prime of x, or f of x is x to the 5th plus 3x cubed, I should just take the derivative of x to the 5th to get what?
5x to the 4th.
And take the derivative of 3x cubed to get
9x to the 2nd.
9x to the 2nd, and that is my derivative. What should this one be? 4x to the 10th should become
40x to the power of 9.
40x to the 9th. 1/2 x to the 6th. The 6 times the 1/2 ought to become a 3, right?
Yeah.
3x to the 5th
5.
plus.
25 to the power x to the power 4.
Then what about minus 2x? Let's think about that. Minus 2x to the 1st, right?
Yeah, just
that ought to be
minus 2. Yeah, just minus 2.
Yeah, minus 2x to the 0, and x to the 0 is just 1. That's just a minus 2. And then what about the plus 3 that was a constant?
0 to the power of negative 0x to the power of negative 1, which is
You're
just
making
0,
things
I
too
think.
complicated.
X over 3.
The derivative of a constant is
0.
0.
Oh.
3 is a constant, its derivative is 0. You're done. Good or no?
Good.
All right. So all those ones we've done so far were just nice, easy ones with nice positive exponents on x for the power rule. But the power rule actually can be extended to work for any real number. So for example, a negative number. If I want to take the derivative of x to the negative 1, I can just apply the power rule, which would give me what? Multiply the negative 1 out front, which makes negative x, right? And then drop the power by 1 to give you x to the
-2.
-2. And this is, if we wanted to, the same as -1 over x squared. Right? This is the derivative of 1 over x, right? And didn't we do that one earlier today? Right? We used the limit as h approaches 0 of 1 over x plus h minus 1 over x all over h. And we got -1 over x squared. Well, this power rule makes it a lot easier, doesn't it?
Yep.
Yeah. What should this next one be?
-4x to the -5th.
-4x -5th, which is -4 over x to the 5th. Hold on 1 second. Sorry about that. What about the next one? X to the 3/2, its derivative should be what?
Three halves to power of x to the power of 1/2. 3x, yeah, 3/2 times x to the power of 1/2.
Okay, or we could rewrite this as 3 square root of x over 2. And what about this one? How would we rewrite square root of x first so that we could use the power rule?
X to the 1/2.
X to the 1/2. And if we want to take the derivative of that, it ought to become 1/2 x to the
-1/2.
-1/2. Everybody good with that?
Yep.
All right. This is an important one. The derivative of root x equals, and we could rewrite this as 1 over 2 root x, right? If I drop the x to the -1/2 to the denominator. So this is an important one that shows up really, really often. That it's kind of just nice to have memorized and know. Everybody good so far with finding these derivatives?
Yeah.
All right. All right, why don't you guys take just a second here and find the derivatives of both of these functions. I'll give you like a minute or two to do this. Everybody feel like they could do that?
Yes.
Yep.
All right, ready, go. So we've got f of x equals x to the 2/3 plus 4x to the -3. So f prime of x, the derivative of f of x, should be x to the 2/3 should become 2/3 x to the -1/3. And what about 4x to the -3? It should become -12 x to the
Or
-4. And if we wanted to write this as 2 over 3 cube roots of x minus 12 over x to the 4th, that'd be good. I would take either answer. Just be able to do both of those. Be able to write it either way, but either one is fine with me. If it was multiple choice on the AP test, though, it could be written either way. They might even also get a common denominator or something like that. So Just beware of that. What about this one?
One over the 5th root of x to the 4th.
Okay, so that became, so x to the negative 4/5, and I'll rewrite it the other way you just said in half a second. But yeah, right, x to the negative 4/5, that's good. And then what about the next one?
10 times x to the negative 6.
Yep, and then the last one there.
6 times x to the 3rd.
Perfect. So we could have written this as 1 over x to the 4/5, or the 5th root of x to the 4th, plus 10 over x to the 6th plus 6x cubed if we wanted to, but like I said, either one of those is a good answer. Everybody doing all right with that?
Yes.
All right. Let's do these two more for you to work on. Ready, go. All right. So first one, root x. We had a rule for that one that I told you would be good to memorize. What was that one? One over
2 root x.
2 root x. And then this one was 5x to the 3/4, right? So what does that become?
15 over 4 times the 4th root of x.
Right, times x to the, well, x to the negative 1/4, right? Or were you saying 4 times the 4th root of x in the denominator?
Yeah, sorry.
Yeah, that's fine. And this one is x to the 1/10, right? Which should become minus, because it's a minus, right? Minus 1/10 x to the negative 9/10. And if you wanted to drop that x into the denominator as a 10th root of x to the 9th, that'd be fine, but this is also good. And then what about this one? This one was x to the negative 1/2, right? So when you take the derivative of that, that should be negative 1/2 x to the negative 3/2. And this next one should be plus 15x squared. Everybody good with that or no?
Yeah.
All right, cool. We feel all right about taking these derivatives? Anybody having any issues? Now is a good time to tell me, because they're just gonna keep getting more and more and more difficult as we go. Everybody's all right? All right. So here are the different notations. There are things called higher derivatives. So there are not just derivatives, but there are second derivatives and third derivatives and fourth derivatives and fifth and sixth and eighth and a millionth derivatives. So just real quickly, so you know the notations for each of them. If you have f of x, its derivative is f prime of x. The derivative of f prime of x is f double prime. The derivative of that is f triple prime. And then from then on, we just write the derivative number in parentheses as a superscript on the f. So this is the fourth derivative of x. Then we'd have the fifth derivative of x, all the way up to the nth derivative of x. So however high we want to go, we can go as many derivatives as we want. Same with y prime, y double prime, y triple prime, fourth derivative of y to the nth derivative of y. Good?
Yes.
All right. If you have y and you write the derivative as dy dx, which is also acceptable, then this, which looks like d squared y dx squared, means the second derivative of y with respect to x. And so the reason why the d has the superscript 2 is to tell you it's the second derivative. And the reason the x has the superscript in the denominator is to tell you that each time you took the derivative, you did it with respect to x, with x as the variable. And everything we're going to deal with right now it's going to match up real nicely. If I have y, it's going to be in terms of x. If I ask you to take the derivative with respect to x. If it's, if y equals 5 theta, then I'll ask you to take the derivative of it with respect to theta. So the derivative variable will match up with the variable you have for now. The third derivative of y, right, with respect to x each time. The fourth derivative, the nth derivative. And then same with these, the derivative, the second derivative, the third derivative, the fourth derivative. These are the most common notations. These top three are far more common than the bottom one, but sometimes they'll write and use the fourth one on the AP test, so I just want you to have been exposed to it. But generally, it'll all be done in one of these three ways. Good or no?
Good.
All right. So let's find some higher order derivatives. Let's find the first four derivatives of 2x to the 5th power. So what's the first derivative? What's f prime of x?
10x to the power 4.
And to find the second derivative, all we have to do is take the derivative of this. So what's the derivative of
40x 3 to the power
40x to
3.
the third? And the third derivative then should just be the derivative of that, which will be 120x squared. And the fourth derivative ought to just be the derivative of that, which should be what?
240x.
240x. Everybody okay with finding those four derivatives?
Yes.
Perfect. All right, let's do another one. Find the first four derivatives of 4x to the 3 halves. What's the first derivative?
Six x yeah 6 square root of x.
6 square root of x, or 6x to the 1/2 is perfectly acceptable. The next derivative should just be the derivative of that. 3 x to the subtract 1/2 negative 1/2. Third derivative ought to be negative 3 halves x to the negative 3 halves. And the fourth derivative of f ought to be what? Multiply the two negative 3 halves together to get 9/4 x to the negative 5 halves. Easy enough or no?
Yeah.
All right. What about this one? You guys do this one. Ready to go. All right, so our first derivative should be what?
Negative 6x.
Negative 6x to the,
First.
nope. We got 3x to the negative 2. We
Negative
gotta
30.
drop
Negative.
down by a power, so negative 3. Everybody good with that being negative 6x to the negative 3?
Yes.
Next derivative should be what?
18x to the power negative 4.
18x to the negative 4. Third derivative ought to be negative 72x to the negative 5, and then your fourth derivative.
360x negative 6.
Everybody good with those four?
Yes.
Yeah.
All right. One more of these. This is the last time I'll make you find the first four derivatives. So what's the first derivative of 50x squared?
100x.
100x. And the second derivative?
100x negative 1.
Nope. This is 100x to the first. So if you take the derivative of 100x to the first, that ought to be 100
Oh, wait.
x to the 0.
Just 100.
Right, and x to the 0 is just 1, so that's just 100. What about your third derivative?
0.
Right, the derivative of a constant is 0. What about the fourth derivative?
I guess 0 again.
And what about the fifth derivative and the sixth derivative and the 100th derivative and the 1,000,000th derivative? They should all just be
0.
0. Everybody good there?
Yes.
All right. Let's use what we've learned about making these derivatives, finding these derivatives fairly easily, and see if we can figure out if the curve x to the fourth minus 2x squared plus 1 has any horizontal tangent lines. So before we get all crazy into this one, let's take a second and think about what does it mean to have a horizontal tangent line? What does that tell you about the slope of the tangent line?
0.
0.
It needs to be 0. And what is the slope of the tangent line? How is that represented in calculus? What is the slope of the tangent line of any function?
Its derivative.
Its derivative. So this is asking, does the derivative ever equal 0 for this function? And if it does, where does that occur? So how do we find out if the derivative equals 0? Well, what do we need to find? We need to find the
Derivative.
derivative. What is y prime? What is the derivative of y?
Four x to the third minus 4x plus 0.
Plus 0, right? We don't need to write the plus 0. Good enough. So we want to know, when does that equal 0? When does our derivative equal 0? Well, how do we solve this? Factor out the common terms of 4x, right? What does that leave me with if I take out the 4x?
X squared minus 1.
All right. And if I want to figure out when that equals 0, we just use the 0 product property, right? 4x equals 0 when x is 0. And x squared minus 1 equals 0 when x is plus or minus 1. So it looks like there are 3 places where this should have a horizontal tangent line. There are x equals 0, x equals 1, and x equals negative 1. Could we find the actual equations of those tangent lines? In order to find the equation of a line, what do you need? You need 2 things.
Point and slope.
You need a point and a slope. Well, the slope is going to be 0, right? Which means these are just horizontal lines, like we said before, which means all we need instead of a full point, we just need a y value, right? So what's the y value when x is 0?
1.
1. What about when x is 1?
0.
Okay, and what about when y, or when x is negative 1?
0.
0. So we should have 2 different lines, y equals 1 and y equals 0. So let's take a look on Desmos at x to the fourth minus 2x squared plus 1. And we'll notice that at x equals negative 1, we have this horizontal tangent line of y equals 0. And at x equals 1, we also had that horizontal tangent line of y equals 0. And up here at x equals 0, we had a horizontal tangent line at y equals 1. So this line is tangent to the function at this point. It means it touches it and stays on the same side of it. Even though it touches the function elsewhere, it's still tangent to the function at this point. And this one is tangent at this point, and it is tangent at this point. Good or no?
Yeah.
And we'll notice probably what happens there at these places where we have horizontal tangent lines. Well, that's a local minimum, or it's a turning point of our function. It goes from decreasing to increasing, or it goes from increasing to decreasing. So that's something we'll continue to look at as we move forward in this unit about derivatives. All right. This will probably be the last one we do today. I'll give you guys a minute or two to work through this one on your own. So let's see if you can come up with an answer to this problem. Ready, go. So once again, horizontal tangent lines means slope of the tangent line is 0. So find the tangent line slope by taking the derivative. What do you get? X squared minus 4. And for horizontal tangent line, set it equal to 0, gives you x equals plus or minus 2. And if we wanted to actually write the equations of those, we'd have to plug in and figure out what is the value of the function when y is, or when x is 2 and when x is negative 2. So what does that give us? It gives us 8/3 minus 8 plus 9, or 8/3 plus 1, which is 11/3. And then this one would give us negative 8/3 plus 8 plus 9. What is that? 43/3. That sound right? I think I did that. Hopefully I did that arithmetic right. We'll find out when we graph it on Desmos. Is that what you guys all, I know I didn't ask you to do this part, but did you all get plus or minus 2?
Yeah.
All right. Cool. So we had, what do we have? We had 1/3 x cubed, right? Minus 4x plus 8. And we can see that x equals 2 and x equals negative 2. That's where it has these turning points where the tangent line would be horizontal. And we came up with what, y equals 13/3. No, was it 11/3? What was it? I don't remember what we got. What did we get?
43/3.
43/3. That sounds better. Cool. Where is that line? Maybe my arithmetic was wrong. Is my arithmetic wrong?
It's
Oh, that's
plus
because this
9,
is
not plus 8.
plus 9. All right. My arithmetic wasn't wrong. I just typed in the wrong equation. And what was our other one? Y equals
11/3.
11/3. Oh, look at that. Those match up real nicely, don't they? 11/3 right there. And 43/3 right there. Good or no? Everybody okay with that conceptually?
Yeah.
All right. Perfect. So that is it for today.